Let's put these time constants to work here and find out how we can do things to further analyze these circuits that we've looked at. We did this in the RC series RC circuits. Let's take a look at them in the series RL circuit. So the exponential formulas. The formulas for exponential current and voltage in an RL circuit are similar to those that we saw in the RC circuit. And the universal exponential curves back in figure 1235 apply to the conductors as well as capacitors. The general formulas for the RL circuits are stated as follows. So we've seen something like this before for our RC network. So we see this for calculating the voltage and the current, where V sub F and I sub F are the final values for the voltage and current. V sub I and I sub I are the initial values of voltage and current, and the lowercase italic letters V and I are the instantaneous values of the inductor voltage and current at a time. Sometimes you'll see in parentheses here T after the I and the V. For increasing current, the formula for the special case in which an increasing exponential curve for current begins at 0 and is derived by setting the initial current at 0. So if we set the initial current at 0 here, we end up with the simplified general expression from the general expression. I is equal to I final times 1 minus E, the exponential, minus RT by L. Using the equation then 1310, you can calculate the value for the increasing inductor current at any instant of time. You can calculate voltage by substituting V for I and V sub F for I sub F in the equation 1310. Notice that the exponent RT divided by L can also be written as T with the inverse now, L over R, which is equal to T over tau, okay, the time divided by the time constant. So again, let's take a look at an example, the easiest way to understand and put this to use. We're going to determine the inductor current 30 microseconds after the switch has closed. So we've got, again, a 12 volt DC source. We've got a resistor, 2.2 kilo ohms, and an inductor of 100 millihenries. So the solution says, again, we calculate first the RL time constant. So tau is equal to L over R, 100 millihenries divided by 2.2 k ohms, which gives us a tau, then a time constant of 45.5 microseconds. So using that then, the terms for the source and the resistance, we can find the final current, I sub F, is equal to 12 volts divided by 2.2 kilovolts, or 5.45 milliamps. Okay, so now we know what the total final current is, and we can put that with our time constant to determine then where the inductor current is 30 microseconds after the switch is closed. So the initial current is 0. Notice that 30 microseconds is less than one time constant, okay? 45.5 microseconds is the first time constant. So the current will reach less than 63% of its initial value in that time. So we've used the expression for initial current at 0. The current in the inductor then is equal to the final current times the difference in I, 1 minus E to the RTL, gives us 5.45 milliamps times 1 minus E to the minus 0.66. Recall, we have to plug our values in for R, the time, and L into this relationship. That gives us the minus 0.66 on your calculator. That becomes your exponential. So we get 1 minus 0.517, okay, 517 thousandths, which gives us 2.63 milliamps. Okay, so that is the current at less than the first time constant. In decreasing current, then, the formula for the special case in which a decreasing exponential current has a final value of 0 is derived now by setting the final value equal to 0. In doing so, the relationship simplifies to current is equal to I initial e to the minus RT over L. This formula can be used to calculate the decreasing inductor current at any instant, as the next example shows. So let's take a look here. What is the current at each microsecond interval for one complete cycle of the input square wave V? So we've got a square wave generator over here, 10 volts at 100 kilohertz, a resistor and an inductor. After calculating the current at each time, sketch the current waveform. So first step, calculate your tau, your time constant, L over R. We get 0.825, 824 thousandths of a microsecond. When the pulse goes from 0 to 10 volts at time 0, okay, that's right here, there's your initial pulse. The final curve then is V final is equal to the source divided by resistance. In this case, we get 14.7 milliamps. So now, if we look at each of the intervals here, 1 microsecond, 2, 3, 4, 5 microseconds. In each case, we're going to run that through the expression here. I is equal to I final, 1 minus e to the RT divided by L, or simply, as you can see, they simplified it, as we saw before, T over tau. So in doing that, that makes the math just a little bit easier. You don't have to enter all those values in. So T over tau. At 1 microsecond, 14.7 milliamps, which is the final current, then times that difference gives us 1 minus e to the T over tau, or 10.3 milliamps. 13.4 milliamps at 2, 3 microseconds, 14.3 milliamps, 4, 14.6 milliamps, 5, 14.7 milliamps. When the pulse goes from 10 to 0 at time t5 microseconds, the current decreases exponentially. Okay, so let's take a look at that. So when we run through this, then we use the relationship I is equal to I initial e to the minus t over tau. Again, we run those values into the expression down here, minus 1 microseconds in this case, divided by 0.824 microseconds. At 6 microseconds, we're at 4.37 milliamps. 7 microseconds, 1.3 milliamps. 8 microseconds, 0.38 milliamps, or 38 hundredths of a milliamp. 9 microseconds, 11 hundredths of a milliamp, and 10 microseconds, 3 hundredths of a milliamp. Okay, so now we have all of our values from 1 to 10. To graph these results, you just put it in a piece of graph paper. You know, it might be interesting is if you put this all together as an example and run it through Excel, create the Excel formulation that would create just exactly this this example problem. If anybody wants to do that, let me know. Okay, so that wraps up this video and some interesting aspects here on using the time constant to solve for the current at any point, you know, at a very, very small amount of time. 10 microseconds, that's 10 millionths of a second.